Okay, this question is about a theme park capsule moving around in a shape that's defined by some parametric equations. We're given x in terms of theta and y in terms of theta, and the first thing we're asked to do is to find dy by dx. Now we know when we're dealing with parametric equations that dy by dx is dy by d theta divided by dx by d theta. So the first thing we need to do is to find those two things. So we take y, we differentiate it, dy by d theta. Sine differentiates to cos, so we get 10 cos theta. And then sine of 2 theta differentiates to 2 cos 2 theta, so we end up with 10 cos 2 theta. Similarly, when we differentiate x, we know that cos differentiates to negative sine, and so we get something very similar, but with negatives. Of course, we can then take the negative outside of the bracket. Now all that remains is to divide these two quantities. And then to divide everything by 10. And this gives us what we were asked to find. We're then asked to verify that the gradient is 0 when theta is pi over 3. Essentially then what we do is we write down dy by dx, but wherever we see theta we put in pi over 3. We get cos of pi over 3 plus cos of 2 pi over 3 divided by sine of pi over 3 plus sine of 2 pi over 3, and of course it's all negative. Now we're trying to show that this is 0, and we know that the only way that a fraction can be 0 is if the numerator is 0. So actually all we have to do is find out what cos of pi over 3 plus cos of 2 pi over 3 is. And it turns out that this is 0. We're then asked to find the coordinates of the highest point A on the path of C. Now we need to realise that if the gradient is 0, then it must be a turning point. So actually this point where theta is pi over 3 must be the turning point A. So actually we know what theta is at A, and so if we go back to the two equations we were given initially for x and y, we can simply substitute pi over 3 into those equations and find out the coordinates of A. So x is going to be 10 cos pi over 3 plus 5 cos 2 pi over 3. That turns out to be 2.5. And similarly for y, we get 10 sine pi over 3 plus 5 sine 2 pi over 3. And that turns out to be 15 root 3 over 2. Now part 2 of the question, we're asked to express x squared plus y squared in terms of theta, and to show that x squared plus y squared is 125 plus 100 cos theta. Now there's a lot of messing about with algebra and trigonometry here. We need to begin by working out what x squared actually is. So when we multiply out these brackets, first thing we get is 100 cos squared theta. We get 50 cos 2 theta cos theta, but we get that twice, so we end up with 100 cos theta cos 2 thetas, and 25 cos squared 2 thetas. Similarly, we need to find out what y squared is, and we just follow the same process through and get 100 sine squared theta plus 100 sine theta sine of 2 theta plus 25 sine squared of 2 theta. Now we're actually asked to find x squared plus y squared, so we need to add these together. We'd end up with a massive line of working, but if we can spot a few things, it makes our lives a lot easier. Firstly, if we add these two terms together, we will have 100 cos squared theta plus sine squared theta, taking 100 outside the bracket as a common factor. But we know that cos squared plus sine squared is 1, no matter what the theta is. And we can apply the same logic to these two terms. We get 25 cos squared 2 theta plus sine squared 2 theta, but cos squared something plus sine squared something is 1. We've then got to add in these two terms in the middle. Again, we can take 100 outside of the bracket as a common factor, but we end up with this fairly horrible cos theta cos 2 theta plus sine theta sine 2 theta. So if we combine the 100 and the 25, we end up with 125 plus 100 lots of cos theta cos 2 theta plus sine theta sine 2 theta. And what we need to show to finish off is that all that stuff in the bracket is just equal to cos theta. And there's a couple of ways of doing this. The first way is to use your compound angle formulae. If we think of theta as alpha and 2 theta as beta, then you'll be able to see from the formula book that sine theta alpha sine beta plus cos alpha cos beta is the same as cos beta minus alpha, and that will all simplify down to just be cos theta. But actually spotting that is going to be quite tricky, and I think what you're more likely to do in this situation is to replace the cos 2 theta and the sine 2 theta with their more expanded formulae. So when we do that, we get 125 plus 100 lots of cos theta, and then we need to remember what cos of 2 theta is. And we can work that out using the formula book. It's going to be cos squared theta minus sine squared theta. Then we're adding to that sine theta, and again we need to look at the formula book and find out what sine 2 theta is going to be. It's going to be 2 sine theta cos theta. Now if we multiply out those brackets, we'll end up with a cos cubed theta. We'll then have a negative sine squared theta cos theta plus 2 sine squared theta cos theta. Now the last two terms are similar there. They're both sine squared theta cos thetas, so we can combine them. We've got 2, take away 1 of them, so we end up with cos cubed theta plus sine squared theta cos theta. Now we're nearly done. We just need to take cos theta out as a common factor. So if we take cos theta outside of the bracket, inside the bracket we're left with cos squared theta plus sine squared theta, which, as we already know, is just equal to 1. So we end up with 125 plus 100 cos theta, which is what we wanted. Now part 3 of the question advises us to use that last result. Here we're looking for the distance between the origin and C, where C can move about on that line. We want to know what's the minimum distance from O to C and what's the maximum. And the way to do this is to think about the general distance. Let's call it R. But we can see from the diagram the general distance R, using Pythagoras, is related to the x-coordinate and the y-coordinate. So r squared is going to be x squared plus y squared. But we already have a formula for what x squared plus y squared is. It's 125 plus 100 cos theta. Now we know that cos theta goes between 1 and minus 1, so the biggest that cos theta can be is 1. And when cos theta is 1, then r squared is 125 plus 100. So r squared is 225, and so r is going to be the square root of that, which is 15. So the furthest away is going to be 15. Now the smallest that cos theta can be is negative 1. And when cos theta is negative 1, then r squared is equal to 125 minus 100. That's just 25, and so r is equal to 5. So the smallest distance between O and the capsule on this ride is 5. Now in the final part of this question we're given another formula and we're asked to use it and our result in part 2 to find the distance OB. Now the first thing to notice here is that at B the x-coordinate is 0. The formula from part 2 is that x squared plus y squared is equal to 125 plus 100 cos theta. But at this particular point x is 0. So we're left with this new formula that y squared is equal to 125 plus 100 cos theta. And that's the first formula we're going to need. The second formula we're going to need is the one that they've given us. Now you'll notice that this is just a quadratic in cos. And so this will give us values for cos that are true at B. So all we need to do is solve this for cos theta. Now this doesn't factorize nicely, so we're going to have to use the quadratic formula. We've got negative b plus or minus b squared minus 4ac over 2a. So cos theta is negative 2 plus or minus root 12 over 4. At b, we know that the value is positive, and so therefore we take cos theta to be negative 2 plus root 12 over 4. Now it's just a case of substituting this into our first formula that's in the box. So we end up with y squared is equal to 125 plus 100 lots of negative 2 plus root 12 over 4. That cos shouldn't be there. Once we stick that into the calculator, we get 101.6. The distance OB is the same as y, which is the square root of that, which is 12.7.